Okay. Here's the question I'm posing. We got voltage versus time. It's a square wave. Kind of like a sine wave, we just smooth it out a little bit. But it's a square wave, so we know exactly what the voltage is here, exactly what the voltage is here, and it changes from this to this instantaneously. That's an ideal, nothing can change instantaneously, but uh, for practical purposes, it pretty much does. Okay. So we're out here driving the voltage. It might be that what we have is a 9-volt battery attached to this circuit. And we've got a switch. And we move the switch, throw it this way, throw it this way, throw it this way, throw it this way. Okay. And maybe we do that very quickly in such a way that the switching takes place pretty much instantaneously. Now, if we're trying to do it at this speed, we're not going to, we're going to spend as much time with the switch off as on. Okay. But we can change the polarity. So we drive voltage here, drive voltage here. You got a device over there. If it works, I got to check that out. To make sure, but we've got a couple of them. They worked last time. Okay. Make sure we get a signal. And then we can use our interfaces to very easily see what kind of current we get. You know how to do that. Okay. What I'm asking you to do is think through what's going to happen. So if we have an RC circuit, where the square wave is very high frequency. Very high, depending on your circuit and so forth, might be 1,000 cycles per second. Okay, so 1,000 of these every second. We could go up to 100,000 every second, I think. But 1,000 is not going to strain any of our instrumentation or any of our devices. So we go up to pretty high frequency. And we go down to low frequency. Of course, we could use our generator, or we could use a switch. Hold it for 5 seconds, switch it for 5 seconds. Hold it for 5 seconds, switch it for 5 seconds. Okay. Throw it this way for 5 seconds, give you positive voltage. This way is connected the opposite way to the battery, so you get enough. Okay. So we go 5 seconds, then 5 seconds, then 5 seconds, or whatever we wanted. That's probably the first thing we will do. Now that's going to affect either the RC or the LR circuit, but not the other. Okay. Why? So the question now, it's a general question. At very high frequency to an RC circuit, what are we going to observe? Now, if we just have resistance in the circuit, this would correspond to whatever your source is here, driving square wave just through a resistor. It's going to look just like this. Okay. If the circuit is like so, got some resistance, and of course it's unavoidable to have resistance, maybe a high resistance, maybe a low resistance. Conceptually, it doesn't make any difference. With a capacitor, or here, same thing, but with an inductor. Very simple circuits driven this way. What's going to look going to be about 5 minutes to think that through. And if you have ideas in that time, just holler at me and share them. Okay, now I want to address this question, the RC circuit. But first we have to understand what we're seeing when we crank the generator. Okay, which we've been doing for 6 weeks. Okay. What happens when we crank the generator? Now, you didn't know 6 weeks ago how to explain what happens. And there are a couple of things that happen with the generator that you still won't be able to explain, like how the rectifier circuit works. Okay, not hard to understand, you get it. Okay, so I'm cranking. And if I'm cranking at a constant rate, I'm generating a constant voltage. Because you can see the gears turning, and eventually they turn a little coil inside a magnetic field. And they're turning that coil maybe 1,000 times per second. Okay, lots of rotation. And now you you're getting 1 rotation per second. And this gear, it drives another gear of about 1/8 the radius. Okay, so that's going to be 8 times per second. Okay, and that's attached to a bigger gear that drives another gear of about 1/8 the radius. So it's about 64 times. That's not 1,000. Okay. And then in here, we've got a coil and a magnetic field, or alternately a magnet inside a coil. I don't know which, it could be either, but I would think it's a coil inside a magnetic field. We know then that the flux, magnetic flux through that coil is changing 64 times a second, right? Well, that's going to produce a voltage. Okay. And it's going to be a constant voltage for cranking at a constant rate. Make sense? So that ought to be an immediate connection because everybody's got a pretty good handle on lenses for it. So, okay. Not in every possible situation, they get pretty weird. But, the basic situation of a coil rotating in a magnetic field, it's pretty clear. Or stationary coil with a fluctuating magnetic field. Okay, now I was driving no current because these leads weren't attached to anything. Now, took one of those in this nostril and one in this nostril. Well, I'm not, but I would get a current. And if I crank fast enough, I might feel a little tingle. Okay. So I get up to 14 volts with this, and I think 14 volts in the tissues of your nose would actually probably hurt a little bit. Not as bad as a clip to your nose, but we don't do that, okay? But what we're trying to do is an RC circuit. Now there's some resistance, okay? And there's other stuff going on, impedance, impedance in the coil circuit, okay? But now if I crank this at a constant rate, oh, it's hard. Man, I'm exhausted already. Now, why? It was really easy to crank a minute ago. Why is it harder to crank? Well, we're going to stop and talk about that. Okay, now I didn't get really great answers there. There were things that were related, but the principle is simply that now that I've got something to drive charge, so that I've completed the circuit, I'm going to have charge flowing. Now I'm creating a potential difference, so charge is being moved through a potential difference. It's a very most rudimentary level. A potential difference is your number of joules per coulomb. So whatever number of coulombs I'm moving through whatever potential difference tells me how many joules of work I do. And you saw how quickly I got exhausted. 8 or 10 joules, I got a rest. Okay, well, not really, but you get the idea. So I'm having to exert a force okay, in order to drive that charge through the circuit.
I'm still cranking at the same rate because the cranking is getting very easy. What does this tell me? Well, it's going forward, yeah, but
we're not interested in that just yet. You know, this thing's just too tight. Yeah, well, I've very quickly got two answers. And they were both good answers. One of them answered my question, and the next one anticipated the subsequent question. And it wasn't a good answer to my question, but it was a good answer. But you can't skip steps. Okay, my point is, so the first answer I got, and actually I asked the second person first, just, give everybody equal chances. The first answer I got was, well, you got your field. And well, fewer coulombs per unit of time, fewer coulombs per crank means fewer joules per crank. Which means I've got to exert less force. And of course, we understand that the number of joules is the product of the force I'm exerting and the distance is exerted. Now I'm exerting a force that's always perpendicular to the radial line. Here's your radial line. Now I'm always exerting force to crank this thing. So I'm exerting a tangential force through a distance that's equal to the radius, to the circumference. Okay. And so let's see, what's that? That's about 610. So every crank I'm going through about a foot. Okay, about 30 centimeters. Ballpark. And whatever my force is, I'm cranking it at 1 per second. I can figure out how much units it takes. But my force is decreasing. It indicates the current must be decreasing because the current is demanding less work for every crank, for every unit of time. Okay? Fewer amps. Power equals current times total, right? Just saying, number of coulombs per second by the number of joules per coulomb gives you the number of joules per second. That's in the transition problems, and I hope that's somewhere deep in your understanding, but okay, so you don't have to drag it out when you need to explain something. Okay, it's part of the tools you need in order to explain what you're seeing. Okay, well, there it is. So this is telling me what? This is telling me for the voltage is constant. I'm cranking at a constant rate. I'm rotating in that magnetic field, changing flux at a constant rate, giving me a constant EMF around the loop. And you need to understand every bit of that. If you're an engineer in this field, then you absolutely need to understand all that. But if you're any kind of an engineer, you need to understand things at that level of graininess, that fine level of graininess where you understand every bit of what's going on. Otherwise, all you're doing is letting AI do your job, and you're not going to have a job because AI is going to take it. Okay. At least I'll be able to call AI when it does something ridiculous. And if you don't have full ready understanding, you're going to be less valuable. Okay. Okay, so there we have that. I'm not trying to scare you with AI. I'm just trying to tell you. Here's how I think you need to learn things. And of course, I always say, ask your engineering instructor. Anytime I make a broad statement like that, he might tell you, that's a bunch of bull. Okay. And he's welcome to. He's the kind of guy that would, which is one reason I like him. Come back and tell me. I don't in the least mind. I want to know when I'm wrong. Okay. So now we have current. What's that gonna look like? Well, see this curve? Have you figured out what it means? Did you figure out what it means before I just explained it and drew it? Did you understand that at the level of graininess? The fine grain level? No, there are things you still need to put together, but they're not difficult things. You just got to spend the time thinking on them and hold yourself to the standard of, I don't know this yet. How can I understand this better? Sometimes you write it out. Sometimes you beat your head against the wall, ponder it every day for a month, and all of a sudden it clicks. All right. So that's for the RC. So what's it look like? Let's say we do our square wave in a low frequency. Yeah, well, I mean, here's the square wave. Okay, here we go. Approximate square waves. I can refer to it. It's pretty hard. All right, we'll figure out why in a minute. Okay. We'll try to understand that at a higher level. So that when we do the differential equations, we know what the heck we're doing them for. And we know what they're telling us. Okay? And the differential equations you're going to be responsible for doing are calculus 1 differential equations, just separable equations. Okay? But we'll also talk about the RLC circuit, which requires some rudimentary technique from the differential equations, of course. You can still understand it. But since you're familiar with it, it's pretty easy to do. Okay, but interpreting it, what you tell it. Okay, so how would I do a low frequency wave? Okay, I'm going to crank. Now, low frequency doesn't mean slow cranking. We do a high voltage at low frequency. Okay. And if we just keep going, it's still going to look like this. It's just our scale. You know, this voltage might be 2 volts, it might be 200 volts. Okay. Curve still going to look like this, assuming we have a capacitor that will handle that voltage. Okay, so what do I have to do? Well, I'm going to start cranking, right? Okay. Now what am I going to do? Reverse it. Already? Well, that'd be a pretty low frequency. I cranked it for at least a few seconds, right? So if I crank it for, that would be one, let's say 3 cranks with 1 second and then reverse. Then reverse. And then reverse. Those things go with it. This time interval from here to here. Haven't paused yet. And what's it going to look like for that first peak? So what I just said, this is just a scratching, but this is a voltage and just this much of the voltage curve. Okay. You might get a curve that looks like this, where it approaches very close to the asymptote to 0. Okay. And of course, this is your current. Or it could be like this, where it doesn't get that close to its asymptote. Why would it not get that close to its asymptote? Because you switched the voltage on it and something else is going to connect, right? That makes sense. Okay, so which one of these is high frequency and which is low? Well, this would be a higher frequency. You change the voltage before it has a chance to get very close to its asymptote. And if you have a very high frequency, it might even pretty much look like this. You might even be unable to see it drop. Okay? But for low frequency, it has time to drop. So this would be low frequency. This is the curve you might get for very high frequency. Make sense? So what does the capacitor filter out? Does it filter out low frequencies or high frequencies? Tell me, low, high. The thumbs are vacillating. Actually, it's going to filter out low frequencies, high frequencies. Current's not going to be changing any. At low frequency, your average, okay, let's just say that this is your current here before changing. Essentially getting no current at all for over half of the cycle, right? So your average current would be very low. Average current is lowest for the low frequency. Okay, that's fundamental. And of course, now I can ask you questions about it. I'd ask you, okay, if the time constant of this is 1 second and the frequency is 1/4 of a hertz, what's the average magnitude of the current? Then you'd have to set up your exponential function for the current, which is very easy. If you know the time constant, it's just e to the negative t over the time constant. Okay. We'll talk about that, but it's very simple once you get used to the idea, and especially provided if you have a good understanding of exponential functions instead of just the rules for differentiating and integrating. Okay. It takes a while to develop a good intuition for that. Okay, well, that's kind of a low brain understanding of why a capacitor suppresses low frequencies. Okay. So what happens with an inductor in each of these cases? Constant voltage for a long time, what happens to the inductor? You then cut off and reverse the voltage. Reverse the voltage, what happens? Now we haven't gotten to reversing the voltage. If we cut off the voltage to the capacitor, it's just going to drop from here to zero, or if it's already pretty much zero, it's going to become really zero, right? And if it's like this, well, it just drops to zero. Okay, because you got no driving voltage. And actually, that's not true with the capacitor because you got charge in the capacitor, and it'll drive the current the other way. We'll talk about what happens. After that. What's the situation with the inductor? Okay, so I asked, you got a solenoid or a set of impulse coils, and you got a current running through it. And what's going on? What happens? Okay. Well, somebody quoted me a good equation, differential equation, LdI dt plus Ri is going to equal whatever. Okay. And it's very good that you know that. Okay, because that's one of the things we're driving at. We've talked about it, so you should know that. So I'm glad you do. That doesn't tell me what's going on. Okay, what's going on? You got a current in a loop. What do you immediately know? You immediately know that Gauss-Savart law tells you if there's a magnetic field through that loop. It's in the direction determined by the right-hand rule. Okay. So we've got a magnetic field in the loop. So now, here we go. Maintain a constant voltage for a long time around that loop, right? For a long time. So it's been going on for a long time. Is the current going to be changing? Is the magnetic field going to be changing? No, it's going on for a long time. Even if that magnetic field takes a little while to build up, it's been going on for a long time, it's going to be built up. So you got a constant magnetic field, and you've got a constant magnetic field in this loop or in this series of loops. What's then going to happen if you throw a switch and cut off the voltage? Or if you reverse the voltage? What's going to happen and why? Okay, where we are in the discussion, I asked you, what if you suddenly turn off, let's say reverse the voltage, what would happen? And immediately, he said, well, the magnetic field would burst. Okay. And I say, well, that's going to happen instantly. Well, yeah, see, nobody objected to that idea. Okay. So that is an objectionable idea. And we're just trying to, again, understand things at a level that makes it clear. Okay. So what happens is you got a magnetic field through a loop in this direction, then you have magnetic field loop in this direction. What has changed? Well, the current has changed. Well, yeah. What else has changed? Immediately, when you think of magnetic field through a loop or some bounded region, some bounded area, okay, you say, well, there's a flux. Flux is a key. Now, somebody said, I don't think it'll change because of Lenz's law. Okay, do you understand Lenz's law to tell me what happens? Okay. Well, I think so, if you think about it long enough. Okay, that's not a bad way to approach it. You know, you got field, so you got a flux, and the flux changes. There's Lenz's law, but what the heck does Lenz's law say? You don't need the guy's name to understand that the rate of change of flux is equal to the EMF around that loop. Okay? And if the name Lenz doesn't invoke what you already understand, then you need to get it to start invoking what you should already understand so you understand it so you don't need the name. Although it's always good to put the name on it if you're talking to somebody who understands what Lenz's law is. Okay? But just saying Lenz's law doesn't solve the problem for you. And taking the step, okay, it's Lenz's law, therefore it's the rate of change of the flow. Okay. That's acceptable. That's a step in the right direction. But if you're going to visualize the thing, you got to just see, okay, there's a flux, it just reversed. Well, it can't reverse instantly because the rate of flux changes the back EMF. Okay? So there's a back EMF involved here. And what therefore happens, well, what does a graph look like at that instant? So let's say, for LR circuit, we got a voltage. It goes like this. Let's just say it suddenly reverses. So we have now current. And of course, we got time on this axis. The current versus time graph going to look like. Okay, so what's going to happen if the voltage stays constant here and then we more or less instantly reverse it very, very quickly at a scale that makes it instant for our purposes, okay? Well, you don't know how long this voltage has been going on already. And it's an inductor and the voltage has to build up, but it's going to eventually reach steady state if it's been going on long. Okay? And that's our premise for a long time. We've maintained a constant voltage. We're eventually going to get to where we have a constant current. Okay? Now we reverse the voltage. What's going to happen? Well, after a long time, whatever long time happens to be, the current will be whatever this voltage dictates. But it can't go from here to here instantly because that would involve an instantaneous change in flux, which would involve an infinite EMF. That's a more or less complete explanation unless you want to go to quantum mechanics. Okay, at least at the level of this course. That's pretty close to the level that I understand too. So, okay. So you have this, and you're going to then exponentially this current. So when the two lines, say you got a very fine pencil, and when the mark made by the very fine pencil merges with the marks made at the target voltage by your very fine pencil, you can say that you now achieve essentially full constant current down here, which will go on until you reverse the voltage again, in which case it'll then, I'll just kind of draw here, exponentially approach this voltage again. Okay. Exponential, remember, means you have a constant half-life. So the question is, in lab, we're going to be able to set this up where we can observe this? Are we going to get data that's tight enough that we can verify whether or not half-life is constant? Now, when we were discussing this, people talk about E to the negative KT and stuff like that. So that's exactly what you use. You got to be careful how you use it. But it's good that you know that and you're thinking about it so that you can then use it to solve some of these problems. Okay. And by completely solve, I mean solve them within the limits of uncertainty dictated by our instrumentation. Okay. There are always weird things going on. I mean, the Earth's magnetic field, fluctuates not very fast, but fast enough that for some measurements that could become an issue. Okay. You have lights, you have circuitry around here. Somebody Turns off the lights, there's a magnetic pulse. Electromagnetic pulse, okay? Makes sense? Okay. So you see how these questions are actually much more complicated than just stupid equations. Equations are easy to solve. And depending how the problem is stated, the interpretation of the equation might be easy. Okay? Okay. Well, I've already talked last time about the equations, and you might think a little more about that. We'll talk about them more related to what we find in lab day after tomorrow. Okay? That makes sense? All right. I'm going to assign you some problems. I've already assigned some problems for chapter 13, I think. And I'll probably assign a few from chapter 14, but we're kind of going to skip over some of the details. So here I am talking about wanting to understand things in fine detail. Saying, well, we're going to skip over some of those fine details. Okay. Mutual inductance and stuff like that. Not hard to understand. We'll talk about it, probably develop it to some extent. Eddy currents, which are kind of fascinating. And we'll demonstrate some of that in lab. It's just you got a pendulum, magnetic pendulum, swinging back and forth in front of a magnet. You have changing magnetic flux through different parts of that metal, which creates little loops of current, which require energy. Therefore, the magnet is exerting a slowing force on the pendulum, which I think is kind of interesting since we observed things moving back and forth between pendulums. I'm not going to spend a lot of time with that, but I'll say, if you're interested in understanding a little more about what's going on here, read about the eddy currents. Okay. Now Eddie has his currents and Billy Bob has currents too. You got eddy currents and Billy Bob currents, and the Billy Bob currents are way beyond the scope of any physics course. Okay. Okay, you're trying to bring me back to the original question. It's a bad idea. Okay, forget about Billy Bob. So this current, okay, if you have a low frequency, then the current pretty much goes on. Then it pretty quickly comes down here and goes on for a little while. Right? Then it pretty quickly, same thing I drew up here, pretty quickly comes back up here, goes on for a little while, comes down here and goes on for a little while. Total area, you would, if you want the power of this circuit, you would actually want to integrate the squared current so everything's positive. But you could just integrate the magnitude of the current over one cycle. And you see that the area between the x-axis and the curve differs from square wave current you would have if you just have a resistor by this little bit of area here, this little bit of area here. Of course, they're not equal. I didn't draw it very accurately. And the shorter this distance, okay, the more quickly you change it, the more this part of the curve sucks out of the area. That makes sense? And the less area you're gonna have, you could try to draw, you contrast that with a high frequency or low frequency. Pretty much gonna be like this. Then like this. Then like this. And if you compare that with the average, square wave is a lot closer to this than it is to this. And if this becomes very short, then you pretty much don't have much of the signal at all. Because you just bouncing back between almost, well, you can look at diagrams and stuff. That's the essence of it. I'd have to draw better diagrams to give you a better explanation. So this is a lower frequency. Okay,
That's for LR.
huh?
That's for LRs.
Yeah, this is the LR. Now up here, it just reverses. Okay. So if you've got a high frequency, if this is your that you would get if the capacitor was absent. If you've got a high frequency, the capacitor doesn't have much time decrease. Okay. Actually, the current kind of spikes down here and then comes back like this. You know, when you reverse the thing, you get a lot more force. So it's going to do something like this. Then it's going to come back to here and do something like this and so forth. Okay. So this would be higher frequency. Then lower frequency, I'm going to get pretty sloppy with where this graph is. If you've got a lower frequency, then here is configuration of your current. And this would be current. Implicitly, time is on the horizontal axis. You got a low frequency, then you got plenty of time for the current to practically disappear. And then when you reverse the voltage, you got to get opposite current. It's going to come like this. Then it's going to come back up, down. And you see, you've got a lot less area under the curve that you get here as compared to the square wave. Here it looks like you got 85% of the area. Here it looks like you've got maybe 30% of the area, 20%. Okay. So again, your capacitor damps out the low frequencies. Your inductor damps out the high frequencies. All this connects very easily to your differential equations that I'll just it's going to solve the homogeneous case. Well, di dt equals negative r over L dt, and you get the exponential function. E to the negative r over L t. cetera. And I worked out the details of that last time. And for a capacitor, you get this is for the homogeneous case. We haven't talked about the non-homogeneous case yet. That your natural, when you have no voltage, you're going to be approaching zero. It's going to be an exponential that as time increases, approaches exponentially approaches zero. So you got this, which is R dq dt etc. You're going to get an e to negative t over r. So I wrote that way too small, but we did it last time. So, just to connect this in some way, there's your e to the negative t over rc there. And over here, be like your e to the negative all over out. Okay. I think, no, that's RC. Yeah. Okay.